Good afternoon. I'm Haroon Serafin, the Deputy Director of the Emerging Technologies Institute at the National Defense Industrial Association. Thank you to all the attendees for your support of NDIA and ETI, and thank you for joining us for today's webinar, Nuclear Weapons Technology 101 with Dr. Bruce Goodwin. This webinar is part of our Technology 101 series, where we will be trying to distill complex technologies into introductory webinars on the science and defense implications. Some administrative remarks before we get started. All attendee lines are muted. If you have a question during the webinar, you can submit your question in the question box in the webinar panel on the right side of your screen. We will do our best to get through all the questions during the Q&A. We're recording today's webinar for members unable to attend and for any member who wishes to review the material at a later date. Within the next few days, we'll post the recording, slides, and answers to the Q&A to NDIA Connect for your review. Now I'd like to introduce our speaker, Dr. Bruce Goodwin. Bruce is a retired nuclear weapons designer. Formerly, he was a senior laboratory fellow at the Center for Global Security Research of the Lawrence Livermore National Laboratory. From 2001 until 2013, he was Principal Associate Director for Nuclear Weapons Programs at Livermore. He then became the Associate Director for National Security Policy Research. He began his career designing nuclear explosives at Los Alamos and moved to Livermore in 1985. He's been responsible for the design and analysis of 5 nuclear tests. He received his PhD in aerospace engineering from the University of Illinois at Urbana-Champaign and his bachelor's in physics from the City College of New York. With that, I'd like to thank Dr. Goodwin for joining us today and turn it over to you for your presentation.
Thank you, Arun. Glad to be here today. And I'd like to apologize to anybody who finds my talk a little too simple today. It is aimed at political science majors, not anybody with a technical background. That being said, let's go to the first view graph. So let me review the current U.S. stockpile. It consists of the following weapons: the B-61, which is both strategic and tactical bomb, the 76, which is the Trident warhead on Trident submarines, the W-78, which is on the Minuteman III. It's currently going into life extension and will become the W-87-1 for the Air Force. The W-80-4 is currently in life extension, and it is the air-launched cruise missile warhead, which will move to the long-range standoff weapon when that becomes available. The B-83 is the modern strategic bomb, the largest weapon in our stockpile in terms of yield and size. The W-84, which is currently in reserve, if you will, for possible future system use. It was designed to be the ground-launched cruise missile warhead, and that missile went away in the INF Treaty, so it is being sustained in stockpile in storage. The W-87, which is originally the MX warhead and is currently on the Minuteman III. The W-88, which is the most recent Trident warhead developed. And finally, the W-93, which is in development at Los Alamos and will be a future Trident warhead. Can we have the next view graph? So, here is a B-61 taken down into its parts. They're mechanically very complicated, but the underlying physics of how these work is pretty simple. Most of this claptrap you see here is electronics that control the bomb itself. The nuclear component is that cylinder to the left of center of the picture here, and is not shown. The parts are not shown. Next view graph, please. Okay, so I'm going to cover the basics here of nuclear design. What is the basis for nuclear fission and fusion, which enable weapons to work? I'll describe fission weapons. I will describe boosting, and then I'll describe the hydrogen bomb, thermonuclear weapons, and the materials that you use in order to enable the processes in these devices. And then we'll get to how a nuclear explosive package actually works. Next view graph. So first, I'm going to have to define some terms, and I'll get fairly simple here. What is an atom and what are they made out of? What are the neutrons, protons, and electrons in atoms? What are isotopes of atoms? A very important concept for nuclear weapons. Then I'll get to what is fission, what is a chain reaction, what is critical mass and supercriticality in a chain reaction, and finally, what is fusion? And when we get those all put away, only then can we get to how a weapon works. Next view graph, please. So atoms are made of protons, neutrons, and electrons. Protons are electrically charged positive particles that reside in the nucleus. Here I've got them colored red. Neutrons are electrically neutral particles that reside with the protons in the nucleus. And the electrons are negatively charged particles that orbit the nucleus. And I've got a picture here of a beryllium-9 atom. It has 4 protons and 5 neutrons, hence the 9 in its name, its weight. And atoms want to be electrically neutral, and so the number of protons is generally equal to the number of electrons that orbit that atom. And it is the electrons, the sharing of electrons between atoms, that determine the chemical behavior of atoms. And so here we have 4 electrons orbiting the 4 protons in the nucleus. Next view graph, please. Let me continue here. As I pointed out, the chemical reactions are moderated or controlled by the rearrangement of the electrons in the orbitals around the atom. Nuclear reactions rearrange protons and neutrons within the nucleus of the atom, hence the term nuclear in the reaction. Next view graph. Isotopes are atoms of the same element, meaning the same chemical behavior of the element. And so they have the same number of protons, but isotopes of the atoms will have different numbers of neutrons distinguishing one from the other. And the really important ones here are deuterium and tritium, which are isotopes of hydrogen, where deuterium has an extra neutron in the nucleus, and tritium has 2 extra neutrons in the nucleus. And these are important for fusion. If you look at uranium-235, a fissile atom of uranium, it has 92 protons. It's at the other end of the chemical chart of the periodic table, and 143 neutrons and an equal number of electrons to protons. Plutonium-239 has 94 protons and 145 neutrons, and of course, 94 electrons. Next view graph. So fission, which is fundamental to all nuclear weapons, has a very interesting history, I think. It was discovered in Nazi Germany by Otto Hahn in 1938, when he bombarded uranium with neutrons, which had only been discovered 6 years earlier by Chadwick in England, and saw that he was producing lighter elements in that process. This was not identified as fission until a year later, when Lisa Meitner, who is a Jewish physicist from Germany who had escaped to Sweden, wrote a paper in which she first used the term fission to describe what was going on and identified the processes that Hahn had produced. Next view graph. I should say that Lisa Meitner warned the British through Niels Bohr of the possibility of nuclear explosives being developed in Nazi Germany after she wrote that paper. Very important political act that she succeeded in. So fission, the process that makes an atomic bomb work, it occurs when an atom of fissile material, say 235 or 239, absorbs a neutron. That atom the nucleus becomes unstable. It basically shakes itself apart, splits into 2 smaller atoms, and in the process gives off 2 to 3 highly energetic neutrons, and makes a lot of energy, 200 million electron volts per fission in this case. I will describe an electron volt shortly, so don't worry about that if you're not familiar with electron volts. And the smaller atoms that get produced vary, and krypton and barium in this example is one possibility. Let's have the next view graph. A chain reaction is a self-sustaining sequence, a series of fission reactions that are caused by the neutrons emitted, if you will, in the first fission reaction. And if you have but that only happens if you have a critical mass. Otherwise, this chain peters out because neutrons get lost to the system. A critical mass is the minimum amount of material, the minimum number of atoms, if you will, needed to sustain a chain reaction. So something to note here is the time scale between steps in this fission chain. 10 to the -8 seconds, 1/100 millionth of a second. And so in a chain reaction, you get a quadrillion fissions in 50 steps in this chain. And that happens, each step takes 100 millionth of a second. So you get a quadrillion fissions in half of a microsecond. That's a lot of energy being produced in a very short time, hence an explosion. Next view graph, please. So if you can run this, these two movies, I don't know if they'll, I guess they won't run, will they? No, it's PDF, I'm sorry. What you would have seen here is the fellow, the hand at the right drops a ping pong ball down into the box, and all these mouse traps start ejecting ping pong balls, which bounce off the box, and eventually all of the traps are fired. And this is essentially a non-nuclear chain reaction occurring. I'm sorry, the movie won't work. Next view graph. So what enables a critical mass? Well, the kind of material is key. You have to have typically plutonium or uranium-235. And the kind of material matters because plutonium is more nuclear reactive than uranium. It has what's called a higher cross section, which makes it more likely to capture a neutron and fission. So you need less plutonium to make a critical mass than you would require of uranium. And I'll get into cross section shortly. It's a metaphor. The amount of material is key here. You have to have enough atoms to sustain, to make that critical mass. And the shape of that material matters. And this is because the neutrons are lost to the chain reaction through the surface of the material. And so the smaller the surface area, the less critical material you need for a critical mass. Now, the compression of the material also matters, hence implosion. If you can force the atoms closer together, they're more likely to intercept a neutron. And so compressing the material through implosion, for example, increases criticality, reduces the amount needed for a critical mass. And any material that you surround the fissionable material with will decrease the critical mass because it acts as a reflector, as a blanket, to hold those neutrons in, to keep them from being lost to the reaction. Next view graph. So material type. Plutonium has a bigger cross section than uranium, so you need less plutonium to make a critical mass. And the metaphor here is a physics metaphor. It's basically saying something that isn't really true, that the atom is somehow bigger in plutonium than uranium, and so is more likely to intercept neutrons. It acts as if it's bigger, so they use that metaphor. And you can see that a bigger cross-section is more likely to capture neutrons. And the metaphor is completed here by physicists by making the unit of cross-sectional area the barn, as in hitting the broadside of a barn. Next view graph. So the amount of material matters. I've got little atoms here drawn. If you don't have enough atoms, the neutrons can just fly right through and not start a chain reaction or maintain it. If you have a lot of atoms, you can't avoid causing a fission chain reaction because the secondary neutrons will go on to fission other atoms. So you need a minimum amount of material to have a critical or supercritical mass. Next view graph. Implosion. If you can force the atoms to be closer together, there's less space between them for the neutrons to slip away, and therefore you need fewer atoms to make a critical mass. Next view graph. The shape matters, as I've mentioned, and a sphere is the best shape because geometrically, a sphere has the smallest surface area to volume ratio of any geometrical figure. So I've drawn here a rough sphere. You can see that the neutrons will cause more fissions before they escape from the surface of that sphere than if the fissile material were in a foil, as I've shown at the right, where the surface area is enormous and essentially all the neutrons get lost and the chain reaction can't be sustained. Next view graph. Finally, putting a blanket around reflects the neutrons back in, just as had you been able to see the movie, the box kept the ping pong balls in and so completed all of the ping pong ball reactions. Next view graph. So let's move on to fusion. And fusion forces small nuclei to merge into larger nuclei. And this is the process that enables the hydrogen bomb. Hydrogen because it uses isotopes of hydrogen, deuterium, and tritium. And in a fusion reaction, if you get the tritium and deuterium atoms moving fast enough, their nuclei, which would normally repel each other, that repulsion can be overcome and the nuclei can be forced together. And what will happen is they'll fuse into a helium atom, and that one extra neutron gets kicked out of the helium atom with a lot of energy, 14 million electron volts. And the whole process produces 17.5 million electron volts of energy. And so fusion of 5 grams, a very small amount of deuterium and tritium, would produce the energy equivalent of 400 tons of TNT equivalent. Next view graph. Both fission and fusion in these cases rely on what's called binding energy variation versus mass number in the nucleus. That doesn't make a lot of sense all by itself. But essentially what you're doing here is the weight of the products of either fission or fusion. In fission, it's 2 smaller atoms and neutrons. In fusion, it's a helium atom, a larger atom, and a neutron. The products weigh less than the atoms that went into the reaction. And that difference in mass is converted to energy through E equals mc squared. And that's where the energy comes from in a atomic or a hydrogen bomb. Fusion is used in a lot of systems in boosted weapons, boosted atom bombs, primaries, hydrogen bombs, and in inertial confinement fusion capsules for energy production. And in fact, all of the elements from hydrogen through iron are synthesized in fusion reactions at the centers of stars. Next view graph. So let's get to energy here. I said I'd describe what an electron volt was, and I'll compare that to everyday experience. Room temperature, 68 degrees Fahrenheit. The equivalent in EV, electron volts, is 0.025 electron volts temperature. High explosive, chemical high explosive burning is much hotter. It's about half of an EV compared to room temperature of 0.025. Now, a single fissioning of a uranium-235 atom produces 180 million electron volts. That's a lot of energy. 100 million times more energy, if you will, than high explosive burning. And fusion, a single fusion process, produces 17 million electron volts. And so this enormous millionfold, more than millionfold increase in energy compared to chemical explosives is what nuclear weapons take advantage of to make very large explosions. Next view graph. So let's compare this to chemical reactions. If you burn a kilogram of coal, and I'm going to use a different unit of energy here, I apologize, you make 30 million joules of energy. That would burn a 10-watt light bulb for about 83 hours. If you fission, if you effectively fission burn a kilogram of uranium, you make 80 trillion joules of energy, and that would burn that same light bulb for about 25,000 years. And this all assumes 100% efficiency, which is not all that realistic. But this is why nuclear power from power plants is so attractive. Next view graph. So, it would seem that if you compare the energy from 1 gram of TNT, which is 2.5 times 10, with 2.5 with 16 following zeros, million electron volts, 180 million electron volts per fission doesn't seem like very much energy. However, there are an enormous number of atoms in a gram of uranium. And so the energy of one fission is about 1/8 million billionth of the energy of a gram of TNT. But 1 gram of uranium contains 3,000 billion atoms. So when you multiply that out, the fission energy in a gram of uranium is 20,000 tons of TNT. And this is why your nuclear weapons are so powerful. Next view graph. So there are 3 types of nuclear weapons. Pure fission weapons. These are the kinds of weapons that destroyed Hiroshima and Nagasaki. Boosted fission weapons, which use the fission explosion to cause a small fusion reaction that then produces an enormous number of neutrons that start extra chain reactions in the original fission explosion, and so boost that fission explosion. I'm amused here, in French, the word for boost is exaltation, which has kind of biblical implications for me, exalting the yield of the weapon. Very poetic. Finally, thermonuclear weapons, the hydrogen bomb, uses the energy of a first stage fission explosion to implode a separate thermonuclear fusion stage and hence produce the H-bomb. Next view graph. So, well, all uranium isotopes may be created, may be equal chemically. Some are more equal than others in a nuclear sense. And so I define a new term here, pair of terms, fissile versus fissionable. Fissile nuclei can absorb a zero energy neutron. So think of this as sort of just sliding the neutron gently into the nucleus of a U-235 or plutonium atom. And it causes the atoms to split in half and fission. Fissionable nuclei, for instance, uranium-238, you have to kick them hard to make them fission. So you make them fission by shooting a very high energy neutron into them, not just adding the neutron, putting a lot of energy in and causing the nucleus to shake itself apart. Next view graph. So here's a list of common fissile and fissionable materials. I've got the 2 most important yellow indicated here, 235 uranium and plutonium-239. And you can see the critical masses are very different. 235 is about 50 kilograms critical mass, whereas plutonium is about 10 kilograms, so 5 times better, if you will. And I've got things like spontaneous neutron produced per kilogram per second here. Clearly, plutonium produces many more spontaneous neutrons, and as a result of spontaneous fissions in the plutonium. And so it makes heat when that happens. And if you hold some plutonium in your hand, as I've had the honor to do myself, it's quite warm to the touch to hold it. Now, there are many other isotopes here. For instance, plutonium-238 is used in spacecraft to make electricity. And you'll notice here that it has a comparable critical mass of 10 kilograms, but it produces almost 1 million times more neutrons in spontaneous fissions and hence gets very, very hot. You wouldn't want to try to hold it in your hand, 553 watts per kilogram. You wouldn't want to hold a 500 kilowatt bulb in your hand, as an example, a 500 watt bulb, I should say. And other isotopes of plutonium, which kind of get in the way of making a nuclear weapon, plutonium-240, 241, 242, and neptunium-237. Let's go to the next view graph. So the 2 weapon materials that are used in fission weapons, plutonium and uranium-235. Uranium-235 has a half-life, meaning it spontaneously decays, and half of it disappears every 700 million years. Pretty slow decay. But since the beginning of the solar system, that's a lot of time, many billions of years. And so only 0.7% of natural uranium remains as 235. Hence, to get 235 for weapons, you have to artificially enrich it to increase its concentration from 0.7% to about 90% for a weapon. Now, 239 has a much shorter half-life, meaning it decays very rapidly. Hence, none of it is left from the beginning of the solar system, 24,000-year half-life. And you have to make it by hand, if you will, man-made. And you do that by putting uranium into a nuclear reactor and producing plutonium. I'll show you that reaction shortly, and then chemically separating the plutonium from the spent fuel, which is a lot easier to do than the kind of enrichment you have to do for uranium separation. And while 239 is desired, you also tend to make those higher isotopes of 240, which have shorter half-lives. And that is a minor complication in making plutonium. Weapons grade plutonium contains less than 8% plutonium-240. Not that you can't use higher percentages of 240 in a nuclear weapon, but it lowers the efficiency and increases the radiation hazard to personnel. Next view graph. So where do you get 235? Well, you have to separate it, and there are 4 ways to separate U-235 out of natural uranium, which is mostly 238. It's difficult to do because they're about 1% or so different in weight, and you have to separate them by weight since they're chemically indistinguishable. The Manhattan Project used 2 different enrichment technologies. The electromagnetic process, where you would spin these atoms, ionized atoms of uranium in a cyclotron, which was called the Calutron, California University cyclotron. And they were built for large-scale use at the Y-12 plant at Oak Ridge, Tennessee. Now, gaseous diffusion ended up being the main way to do this. It was invented by the British and transferred to the United States. It was built for large-scale use at the K-25 plant at Oak Ridge. And there you're forcing a gas of uranium through porous filters, and the little tiny pores more easily let the 235 through than the 238. And so with a cascade of these, you could separate the 235 to the 238. And until a few decades ago, this was the sole source of enriched uranium for the US nuclear industry. Next view graph, please. Modern separation occurs largely in gas centrifuges, and you have a picture here of the the centrifuges in Iran. The separation here, again, depends on mass difference. You spin a gas of uranium to very high speeds in these centrifuges. The heavier molecules go to the outside, the lighter ones tend to go to the inside, and you scoop them off. Now, the degree of separation in any one centrifuge is fairly low, and so you need a cascade where you take the enriched from one, put it into the next, quite literally scores of centrifuges in a cascade to get to the high yield concentrations that you need for a weapon. Now, the best way to separate is atomic vapor isotope laser isotope separation, AVLIS. And here you use very special lasers to knock the electrons off of the outside of a 235 atom, but not a 238 atom. So now the 235 atoms are electrically charged, and you can pull them out with an electric field. And so you get very large separation in a single step. A large demonstration project of this was built at Livermore in the 1980s, but quite honestly, gas centrifuges had taken over the world. And so this very good process basically commercially failed. Next view graph. So where do you get 239? It does not occur in nature, as I've pointed out, but what you do is you can breed it in a reactor from uranium-238, which is the most common uranium atom. And so here what you do is you put 238 into a reactor, you hit it with a neutron, it absorbs that neutron and becomes uranium-239 isotope, which is unstable and decays in a very short time to neptunium-239, where a proton in the uranium-239 nucleus emits an electron to become a neutron. And so, a neutron emits an electron to become a proton. So the the uranium goes up in the chemical charts to neptunium by that process. And then the neptunium, in a little bit longer period of time, will similarly, a neutron will emit an electron to become a proton and jack that neptunium up in the chart to plutonium-239. The 239 is what you want, but if there's some likelihood that as it sits in the reactor, it will absorb a neutron and become plutonium-240, and then 240 could become 241. And so you only want to leave the fuel rods in for a short period of time to minimize the higher isotopes of plutonium getting produced, reprocess the rods, get the plutonium out, and put them back in the reactor to keep making plutonium. Next view graph, please. Now, going back to fusion here, as I pointed out, deuterium and tritium can fuse to make energy. And again, the products of the DT fusion weigh less than the DT that goes into them. And so the difference in mass gets converted to energy through E equals mc squared. Now, tritium has a commercial industry involved with it. And if you want to buy tritium, you can get it for about $30,000 a gram. As I pointed out, the fusion of 2 grams of D and 3 grams of T produces about 400 tons of explosive energy. And at 100% efficiency, that's 80 kilotons per kilogram of fusion energy, as compared to 17.5 kilograms per kilogram for a fission reaction. And this sort of almost 5-fold increase in yield per weight is what makes hydrogen bombs much more attractive than atom bombs. Next view graph. Deuterium occurs naturally in water in very small amounts, and you can get it by separating it from natural water through chemical exchange, distillation, or electrolysis. The Norwegians, before World War II, produced deuterium because they had an excess of electricity from their hydro plants. And this is what was destroyed by the British in order to keep deuterium out of the hands of the Nazis in World War II. Tritium does not occur in nature because of its very short half-life, 12.5 years. And so you have to make it in reactors using slow neutrons. And here what you do is you take the isotope lithium-6, which is a light metal, put it in a reactor, and basically fission it with neutrons to make natural helium and the tritium isotope of hydrogen. Next view graph, please. So let's talk about how you make a critical mass. There are at least two ways to do this. The original approach was gun-assembled fission weapons, and that was what was used in the Little Boy device over Hiroshima. It's about a 15 kiloton weapon. And here you used a propellant to accelerate 2 subcritical masses of U-235 together to form a supercritical mass that would then fission explode. Next view graph. Implosion is a much more efficient approach, and this is what was used in the first nuclear test, the Trinity explosion at Alamogordo, New Mexico. And it was used in the Nagasaki Fat Man device that destroyed Nagasaki, a 20 kiloton device. And here you take a subcritical mass of plutonium, the green in the center of this picture, and you surround it with a large amount of chemical explosive, and then you very precisely detonate that chemical explosive from the outer spherical surface, driving a explosive-driven shock wave in to squeeze the plutonium, force the atoms closer together to form a supercritical mass that can then be made to explode by injecting neutrons into it. These are the basic approaches to the original atomic bomb. Next view graph. So the yield in these types of weapons is very sensitive to when you shoot the neutrons in to start the fission chain reaction. They must be injected at a very precise time in the implosion, not too early and not too late. And some yield can, in fact, be produced without shooting neutrons in, since there is a background of neutrons that naturally occurs, for instance, in plutonium. So what I've plotted here is kind of a complicated graph, is time across the bottom in millionths of a second, actually. And the vertical axis, the y-axis here, is neutron multiplication factor. That is, if you will, the rate at which fissions are occurring. Now, at 0, there are no fissions. If you go above 0, which is where criticality occurs, you become more and more what's called supercritical, meaning the rate of fissions is occurring faster and faster. So this curve is plotting fissions per millionth of a second. You go above 0. If you were to put the neutron in that starts the fission chain reaction, when it first crosses 0, you'll make fission energy, and that fission energy will expand the metal, lowering its criticality back down to 0. And so the yield that you get, which is fissions per millionth of a second times time in millionths of a second for total number of fissions, is that little triangular area there down on the left, the gray area, and it's a very low yield. That's called pre-initiation. That is not good for a nuclear weapon. Ideally, you want to start the fission chain reaction at the peak of supercriticality, the top of this curve. And if you inject the neutrons at precisely the right time, you'll get the maximum fission explosion yield from the weapon, which is that larger gray area under the curve where you start producing energy. The energy causes the criticality to decline to 0. And so the area, the fission rate times the time is total number of fissions is that larger area. So timing of the initiation pulse of neutrons is critical to the proper operation of a nuclear weapon. Next few graphs. So, as I mentioned, Trinity was the first test of a nuclear device. It was called the Gadget on July 16th of 1945. You can see it down here in the lower right before the test. And all of those cables that you see running around that sphere are the electrical cables that started the detonation on the outside of the chemical high explosive that had to be very, very precisely timed to produce a perfectly spherical implosion. Next few graphs. The current stockpiles of the world, at least of the P5 states, that is the United States, the UK, France, Russia, and China. P5 defined under the comprehensive test ban, under the test ban treaties, consist of thermonuclear devices. Thermonuclear refers to fission because the way you get those deuterium and tritium atoms moving fast enough to fuse is by making them very hot, hence thermo and thermonuclear. And again, the fission of light elements occurs most efficiently at high temperatures, think the center of the sun, and it does release then an enormous amount of energy. Next few graphs, please. Modern P5 weapons, again, employ both fission and fusion. Fission weapons can be gun assembled or solid packed, and fusion weapons can be boosted fission weapons, and I'll describe that, and thermonuclear weapons, that is the hydrogen bomb. The next few graphs, please. Now, let me tell you how a boosted fission weapon works. And you boost fission weapons in order to significantly reduce the weight and the amount of fissile material that you need to make the weapon. So it uses deuterium and tritium that are put into the imploding core of a fission weapon in order to generate neutrons to increase the fission yield. So a small amount of D and T fusion releases a greatly increased amount of plutonium fission yield. So think of this as fission produces fusion, enhances fission, fission, fusion, fission. And the fission material is in a hollow shell. I've illustrated that here, a hollow shell of plutonium surrounded by a stainless steel case. The deuterium and tritium is injected into the hollow at the center through what's called a pit tube. The whole assembly is called a pit. The high energy fission fragments from imploding that plutonium shell down and making it go supercritical explodes. It directly compresses and heats the fusion fuel to fusion detonation. Fusion detonation occurs much faster than fission explosion, and so the enormous number of neutrons that get produced in the fusion reaction then very quickly boosts the number of fission chain reactions, increasing the yield of the weapon enormously. Next view graph, please. So a staged hydrogen bomb, a thermonuclear weapon, will give a very high yield in a missile deliverable warhead. Here we have a cartoon of what I'll call a Teller hydrogen bomb. Edward Teller and Stanislaus Ulam came up with this configuration where they placed a atom bomb inside of what's called a radiation case, a bottle, if you will, that's opaque to X-rays, with a fusion stage next to it inside of that bottle, that X-ray opaque bottle. So the primary goes off and fission explodes. It might be boosted and produces tens of kilotons of yield, perhaps. And if you think of a small slug of metal with a kiloton of yield or more inside of it, it gets very, very hot. And it glows. It doesn't glow red or white hot. It glows in the X-ray spectrum. Those X-rays come out and try to go in all directions, but there is a X-ray opaque bottle around the whole thing that contain those X-rays, prevent them from going out. And the X-rays can only flow in the direction of the fusion stage. They flow out and around the fusion stage. They heat it up. We're talking enormous temperature, millions of degrees of temperature here, and heat up the outside of the fusion stage, causing its outer surface to blow off as a plasma. And if you think about it the way a rocket works, if the exhaust goes one way, the rocket goes the other way. Here, the exhaust is going out spherically around the secondary, driving shock waves into the secondary to implode it and directly heat it, compress it, and drive it to fusion detonation, producing the hydrogen yield of a hydrogen bomb. So the yields of a primary can be kilotons to tens of kilotons, but the yield of the hydrogen bomb can be hundreds of kilotons to megatons. Next view graph, please. So where does Livermore come into all of this? Well, Los Alamos detonated the first hydrogen bomb in 1952. However, they worked well, but they were gigantic. As an example, we have a picture here of I believe, the first deployed hydrogen bomb next to a B-36 bomber. It's weighed tens of thousands of pounds, and the largest aircraft in the world at the time, the B-36, could carry one. Livermore was developing a few other ideas. In fact, our first three nuclear tests catastrophically failed to work, but the ideas were pretty good nonetheless. And so in the summer of 1956, the Navy held an anti-submarine warfare conference in Woods Hole, Massachusetts, codenamed NOBSCA for the lighthouse at Nobsca Point. Edward Teller attended, and he proposed a radical new warhead concept that would produce a 30-fold increase in yield to weight. The Navy decided at that meeting, on the basis of his proposal, to change its submarine-launched missile technology to Polaris systems, which are very small compared to their plan to use liquid-fueled Jupiter missiles originally, and were enabled to go from 3 to 4 missiles per submarine to 16, and to use solid fuel, which was very, very much safer. The Atomic Energy Commission and Livermore then worked in parallel with the Navy to design and produce a radical new miniature warhead, the W-47, the first modern miniature hydrogen bomb. So for comparison here, I have a picture of a standard engineer standing next to a state-of-the-art 1956 Los Alamos H-bomb. Next view graph. Whoops, back. Let's go back one. And here you have that same standard engineer standing next to the W-47, circa 1958, the first Polaris warhead, the first miniature H-bomb. And then 6 years later, standing next to the Poseidon warhead, a factor of 4 smaller even than the 47. So this miniature technology was developed at Livermore between 55 and 58. John Foster, my hero, developed the first modern miniature boosted atom bomb. Harold Brown, who became Secretary of Defense eventually, developed the modern thermonuclear secondary, and Herbert York made a major contribution, which unfortunately I can't describe, but very key to making this work. So this breakthrough was made via the fact that Livermore had a unique close linking of experiment and high performance computing, which was new at the time. This technology dominated nuclear warheads in the 1960s and was transferred to Los Alamos in 1973, and it is now ubiquitous in the US stockpile. Next view graph, please. Give you some idea of how miniaturization actually looked without showing you the weapon. We have a picture here of the assembly engineer eating his lunch, a tuna fish sandwich, on top of a suitcase which contains the nuclear test item for the first miniature atom bomb, the Tesla nuclear test back in 1955. Quite a reduction from that multi-10,000-pound weapon of 1953. Next view graph. So let me wrap this up. Nuclear tourist. There are places you can go to see where all of this happened. Particularly the Los Alamos Laboratory in New Mexico has a wonderful museum, and you can visit the Boys Ranch House where much of this work was done. Kirtland Air Force Base has an outstanding National Atomic Energy Museum. At Alamogordo, you can actually visit the site of the first nuclear test, the Trinity site. It's open 2 days a year, the first Saturday in October and in April. You have to make an appointment, obviously. Oak Ridge National Laboratory you can view the X-10 nuclear pile where plutonium was produced. You can, in Nevada, take a tour of the Nevada test site. Have to make, again, an appointment there through this website. And in Las Vegas, they have an outstanding atomic testing museum that you can visit. And from the comfort of your home, you can visit the Livermore Atomic Nuclear Test Archives online with this site that I list here. And finally, at Hanford, the B reactor is viewable at the Manhattan Project National Historic Park. Let's go to the next view graph. And that's the last view graph. Let me go to a couple past this. If you could just kind of flip down one more. To give you some idea of how many nuclear tests the United States needed to execute to get to where we are today. Here's an aerial view of Yucca Valley, where most of the underground nuclear tests were performed and many of the atmospheric tests. We did 1,054 nuclear tests in order to develop and sustain the modern stockpile. But we've developed the technology to do all of this now without nuclear testing, but that is in itself an entire other talk. So thank you for your time here, and I'd like to see if I can answer any questions that you may have.
Thanks very much, Dr. Goodwin, for that presentation. I apologize to you and to the participants for the technical difficulties there. I think we'll go a little bit into injury time and go over a little bit and try to answer some of these questions. I also want to point out that that mousetrap fission video that didn't run, I think you can find versions of it on the web if you just Google mousetrap fission. I think that's right. Yes. So let me just go through some of the many questions we got here. One question is, the original researchers who were thinking about this, how did they produce the neutrons for the original reaction?
Oh my gosh, I'm not sure I know how they produced it. The way that we produce them today is typically with a thing called a diode, a 2-element vacuum tube. You will load tritium onto the onto the anode of that tube and deuterium onto the cathode. You heat up the anode, and so you make the tritium atoms into ions, which are electrically charged by heating them. And then you put a very large voltage across the anode and the cathode, accelerate the tritium ions into the deuterated cathode, causing fusion to occur, which produces 14 MeV neutrons. And so you can do that very precisely. You can pulse the tube and produce pulses of neutrons whenever you want them. I'm not sure how Otto Hahn made neutrons back then, or Chadwick for that matter, in the 30s.
Another question, how do tactical nuclear weapons work? Are they all fission? Are they small fusion bombs? What's their engineering?
Well, it very much depends on the yield that you want from the tactical weapon. They could be gun assembled, they could be small boosted weapons. They're not typically unboosted implosion weapons, because those are gigantic and are rather unwieldy for tactical use. And you should keep in mind that a weapon can be made to have different yields, and that in fact a weapon can be strategic or tactical depending on its yield and its delivery mode. The B-61, as an example, is both strategic and tactical.
There's a few questions which are sort of vocabulary glossary questions. So I'm going to run through them all for you one by one. Could you define a pit?
Pit. Okay, the pit is the element inside of an atomic bomb that gets imploded in order to produce a supercritical mass. So a pit would contain, say, uranium, or more typically plutonium. It might have a cavity in the center for deuterium and tritium, depending on whether it's boosted or not. And the pit then is surrounded with chemical high explosive to produce the implosion.
Dirty bomb.
A dirty bomb. A dirty bomb is an atomic weapon that has isotopes of materials that produce, when they get irradiated with the neutrons from an atomic bomb, produce highly radioactive isotopes, which then will contaminate an area to make it, if you will, uninhabitable to human beings. We in the US do not have dirty bombs.
And that ties into another question. Could you talk about the weapons effects here, blast and radiation, and whether you can tailor for them and how we do that?
Yes, well, the effects are either X-ray effects from that shining pit, producing the fireball that you see typically in a nuclear test, the neutrons that come out from the fission explosion and or fusion explosions. And that fireball ionizes the atmosphere, and that drives enormous shock waves out, which is the blast effect that you get from a weapon. And so all three can be used. They can be tailored, for instance. I think everybody's heard of the neutron bomb, which was designed to preferentially produce high energy neutrons rather than blast or from the weapon. And those were intended to destroy tank crews, Russian tank crews coming into Germany should they have invaded the West, because the neutrons would easily penetrate a tank compartment and kill the crews inside, as an example of an enhanced radiation weapon.
Two other terms we hear are low enriched uranium and depleted uranium. What are those and how are they used?
Okay, well, depleted uranium is almost entirely uranium-238, which is the non-fissile isotope of uranium, uranium-235 being the fissile isotope. So depleted uranium is quite literally depleted in uranium-235. It's, if you will, the tailings that come out of an enrichment process for uranium. Enriched uranium can be low enrichment or high enrichment. High enrichment is, on the order of 80% or more used for weapons. Low enrichment, is of the order of a few percent to tens of percent for use in reactors, which operate obviously on slow neutrons versus weapons that operate on fast neutrons.
Here's a question about current events. In September, it was announced that a nuclear plant in southern Ukraine was shut down. What's the process by which that shutdown occurs, and how safe does the plant then become to surrounding areas?
Well, I have to confess I'm not a reactor engineer, so I'm perhaps not the best person to answer that question, but I will try. When you shut down, and my understanding is that when you shut down a nuclear plant, you want to bring it down slowly. The reactors produce a great amount of heat, which is used to boil water to make electricity. You do not want to abruptly shut the reactor down because the core will remain hot for a long time. And in principle, you could end up with an abrupt shutdown, say with an attack on the plant, having a steam explosion. And that's sort of what happened at Chernobyl. And that's not a good thing. So when you often shut reactors down, you do it slowly, you bring them down, you lower the heat load in the core to bring it to a stable point where it will not produce a steam explosion.
And we'll have one last question, and it's on proliferation. We've heard different breakout timelines for Iran's nuclear weapons program. What accounts for those different kinds of estimates? And what would, if you or us non-experts, what should we be looking for in the public accounts, press accounts to separate the reality of the situation from everything else?
Well, I'm not sure that you can see in the press things that would allow you to separate reality from fantasy. But breakout depends on a number of things. It depends on your ability to manufacture pits, as an example, and your ability to manufacture pits depends on the availability of fissionable materials and having enough of fissionable materials. So I think with Iran, you want to keep an eye on enrichment, since that appears to be their approach to making atomic weapons with uranium. I would also think that you would have to keep an eye on their reactors, because they might be trying to use depleted uranium to make plutonium. So your readiness, if you will, to make a weapon depends on a number of nuclear and non-nuclear technologies, your ability to make precision chemical high explosive systems for the weapon. I could be a little bit controversial here and say probably the most ready nation to break out would be Japan. They have 11 metric tons of weapons usable plutonium in country, and they certainly are one of the most advanced technological countries in the world, though I don't think they're motivated to break out, even though they would be in a position to do it very quickly.
Okay, with that, I'm going to close the session. I want to thank Dr. Goodwin for his great presentation and answering the questions. Thank everyone for their attendance. Apologize again for the technical difficulties. We're going to post the full recording on the YouTube site soon, as well as NDIA Connect as soon as possible. If you have feedback about the series, the Tech 101 series, especially topics you'd like to see us cover in the future, please email us at etia@ndia.org. I want to take this opportunity to highlight some upcoming events for the Emerging Technologies Institute. The next session in this Tech 101 series is on Cloud 101 with Matt Bukovic from Carnegie Mellon Software Engineering Institute. We are participating with the Science and Engineering Technology Division in their Executive Breakfast Series. The featured speaker here is from OSD's Research and Engineering Office, Dr. Ben Petro. He's going to be talking about the DoD laboratories and how industry and universities can partner with the laboratories. And then we're working on a software as a modernization priority workshop, which will be November 14th in person at NDIA. If you've got questions about any of those, please email us at etia@ndia.org. Registration information on all these things is on our website. You can reach out. And so with that, I want to thank everyone for participating. Thank Dr. Goodwin again, and I'll call the session to a close. Thank you.